For Module 18b, we're going to continue on with buffers, but we're really going to start looking at how are we determining the pHs. We need to talk about the common ion effect and be able to predict the effect of adding a salt of a weak electrolyte to the electrolytic solution, seeing how this is going to affect your pH. You should know and understand the Henderson-Hasselbalch equation. pH equals pKa plus the log of the concentration of base over acid. Now, I don't require my students to use Henderson-Hasselbalch, except that it's an incredibly useful equation, and you will see it elsewhere. You'll see it in other fields, biology, biochemistry, chemistry, etc. In general, you need to understand this equation. Even if you don't want to use it right now, that's completely fine, but you need to understand where it comes from, how it comes together, and honestly, once students understand it, they tend to like it better than doing it the other direction. But you also need to know its limitations and understand when it's appropriate to use and when it's not. You should also be able to determine the most appropriate substances to prepare a buffered solution at a given pH. So first, stoichiometry. When we're solving buffer and titration problems, we need to treat the reaction as either a stoichiometry problem that goes to completion or an equilibrium problem. Stoichiometry problem, Gen Chem 1. We've got a single-headed arrow. This is going to be your neutralization reaction. You're going to use the BCA before change after table, which I call a mole table, not an ice table. The reason I say mole table is that everything is in moles. In an ice table, everything's in molarity. So you have to use moles or millimolar, not concentration. It is a limiting reactant problem. So it's back to chapter 4, chapter 5 when we learned limiting reactions, but instead of setting it up like a regular limiting reactant problem like we taught you in first semester, we're setting up it as a mole table. It's actually a faster way to do a limiting reactant problem and to see how much access remains. We just don't normally teach it in first semester because you're learning so many other things first semester that it's hard to grasp this as well. Because it is a limiting reactant problem, though, all the limiting reactant is completely consumed, and so therefore the change in the BCA line never has minus X or plus X. We know the values. Then, once you've completed your BCA table, you feed the results from the from the after column into the equilibrium step. So equilibrium, we've covered this in Gen Chem 2. This is where you use your double-sided equilibrium arrows, not a single-headed arrow, and we use an ice table. We use concentration, not moles. Specifically, we're looking at molarity. There's a lot of good shortcuts we can use. We can often avoid an ice table and use things like the Henderson-Hasselbalch equation. We also need to remember that Kw is equal to the concentration of H3O plus times the concentration of OH minus. That can get us so many places. We can always use that conversion. So let's work a series of examples. What is the pH change that occurs when 0.010 moles of HCl is added to 1 liter of pure, meaning unbuffered water? We assume no volume change. Why do I say assume no volume change? I say that because, to be completely honest with you, when you are mixing these solutions, you're going to have to figure out their new volumes and therefore their new concentrations. We're keeping the same number of moles. Remember, your molarity is dependent upon the numbers of liters of solution you have. So when I add different solutions together and their volume changes, their concentrations change. When we say assume no volume change, it's just making the math a little bit easier for that example. But I want to know what is the pH change that occurs. So if that means, if I have pure water would have a pH equal to 7.00. Why? Because in pure water, the concentration of H3O plus equals the concentration of OH minus, and each one of these equals 1.00 times 10 to the minus 7. If I took the pH of that, I would find it to be 7. Remember, Kw is equal to H3O plus times OH minus, which is 1.00 times 10 to the negative 14. If I solved for just the concentration of H3O plus, I would find that it equals 1 times 10 to the minus 7, and the pH would, negative log of that, the pH would be 7. But I add 0.010 moles of HCl to this. I want to know the pH of that solution. If I take 0.010 moles of HCl and I add this to a 1 liter solution, assuming no volume change, that would give me a 0.010 molar HCl solution. The pH here, pH of 0.1 molar HCl is equal to 2.00. This question's asking me, though, what is the pH change when this happens? So my change in pH, it started at 7.0. We do final minus initial. We finish at 2, we start at 7, negative 5.00. The pH plummets by 5 pH units. You may ask why I put the 2 here in front instead of the 7, instead 2 minus 7, and that's because the delta here always means final minus initial. So the final pH minus the initial pH. We could say your pH plummets by 5 pH units, the pH is decreased by 5 pH units. When I add in 0.01 moles of HCl to a 1 liter of pure water, I see the pH decreased by 5 pH units. The new pH is 2.0 or 2.00, whatever you'd like to say. We see a large decrease in pH. That's the most important part of this whole example, is that our pH is 2.00, very, very low. In contrast to that example, though, what happens if I take that 0.010 moles of HCl and I add it to a 1 liter buffer that contains 0.1 molar acetic acid and 0.1 molar sodium acetate? We're again going to assume no volume change, and it tells us the Ka of acetic acid, and that's 1.8 times 10 negative fifth. The key to solving this is to first do that stoichiometry step, meaning the mole table. Then feed those results into an equilibrium step. We can also simplify this and recognize our acetic acid is Ha, and our sodium acetate, sodium is a spectator ion, acetate is our A-. So we have a weak acid conjugate base buffer system. What's going to happen when I add, let's first look at the pH of the system before we add the acid. Before I add acid, I have my acetic acid plus my water in equilibrium with my conjugate base, in this case acetate, and H3O+. It tells me that I'm starting out with a 1 liter solution containing 0.1 molar acetic acid and 0.1 molar sodium acetate. I have approximately no H3O+ present at the start. Remember, we say approximately because just by water we have 10 to the minus 7th molar, but it's such a small concentration that we can probably ignore it from the start. We always say minus X on the reactant side plus X on the product side. Why did I put HA over here and A- over here and not flip it the other way? Because I was given Ka. In order to use Ka, I need to have H3O+ on my product side. So I'm making my life easier by doing that. But X's are always minus on the reactant side, positive on the product side. This is in the equilibrium to start, so it's not, from a bird's eye view, it's not like, oh, well, we do have some acid reacting. How do I know I'm not creating too much base? The ratio, the Ka takes care of that for us. We don't have to worry about that. It's still minus X on the reactant side plus X on the product side. At equilibrium, I get 0.10 minus X, 0.10 plus X, and X. Set up your Ka expression. A minus, H3O plus, and HA. I know that my Ka is equal to 1.8 times 10 to the minus fifth, and this is equal to 0.10 minus x, plus x times x divided by 0.10 minus x. Just like in the previous chapter, we assume that x is really small as compared to that 0.1 molar value we have for the acid and conjugate base. Because our Ka is so small, the amount that actually dissociates is probably pretty little. So we assume this goes to 0 and this goes to 0, which simplifies our equation. We have 1.8 times 10 to the minus fifth equal to 0.10 times x divided by 0.10, which means x is equal to 1.8 times 10 to the negative fifth. But again, x equals the equilibrium concentration of H3O plus, and if I was to find the pH of this, the pH would be equal to 4.74. So initial, the buffer is at 4.74. This is actually known as the pKa value of acetic acid, because remember what pKa means? Negative log of Ka. Well, you just took the negative log of the Ka value. We'll see this on a titration curve as well, but this is quite important in chemistry. What this means is that when the concentration of a weak acid equals the concentration of that weak base, they're equal in solution, pH equals your pKa value. So we got the initial pH, but I want to find the pH after the addition of HCl. I need to erase all this because I don't have space. And if I'm going to add acid to it, I need to first do a mole table. So, pH after adding acid. Mole table. Or BCA or B delta A, whichever way you want to remember it. I know I'm taking a strong acid, H3O plus. You could write H plus as well. I write H3O plus because HCl plus water gives you single arrow H3O plus Cl minus. So my H3O plus is going to react with the buffer. Acids do not react with acids. Acids react with bases. So this H3O plus must react with the conjugate base. These neutralize, and what's going to happen is the acid is going to donate a proton, the base is going to accept, and I'm going to reform my weak acid plus water. B, C, and A. These are moles. Initially, my before is how much did I actually add? Well, I'm adding 0.010 moles of H3O plus. For A minus, I have a 1 liter solution of 0.1 molar. So 0.1 moles of CH3COO minus. You actually have to figure out the correct number of moles here. I understand molarity tells you how many moles you would have if you have an entire liter. If we did not have an entire liter, you would have to do the math to figure out the exact number of moles. We see that in here, though, we do have 1 liter, so we have 0.1 moles of A minus. And don't forget, we still have, not technically even, in solution we have 0.1 molar, or 0.1 moles of acetic acid also present. And water does not factor into this table. We now compare these two numbers in the reactant side. We know that they react in a 1-to-1 fashion. So whichever one is smaller is going to be the one that's going to run out. Minus 0.010 moles minus 0.010 moles plus 0.010 moles. Why minus? Because that H3O plus reacts with the A minus. Y plus, because it's producing HA. After that, we have no strong acid remaining. We have 0.09, let's see, 0.09, that is my sig figs, moles of my conjugate base left over. And now we have 0.11 moles of my weak acid. You need to recognize that this means you have a buffer. You have both the weak acid and conjugate base present. You have a buffer. Now you're going to feed this information into an ice table. So, HA plus H2O in equilibrium with A minus plus H3O plus. I just had HA on the product side though. Why am I writing on the reactant side? It doesn't matter. You can write either HA or A minus on the reactant side. They're both present right now. Either one can go on the reactant side, the other one has to go on the product side. They are not on the same side. It doesn't matter which side you write it on. But I'm writing the HA on my reactant side so that I can have H3O plus on my product side so that I can use Ka. I don't want to have to convert to Kb. If I put A minus on my reactant side, A minus reacts with water to form HA plus OH minus. In that case, I would have to use Kb. That's fine, you're welcome to do so, but I don't want to because I'm given Ka and I don't want to have to convert if I don't have to. The less conversions I have to do, the less mistakes I'm likely to make. Now you do need molarity here. I have 0.09 moles of A minus in 1 liter, which means I have 0.09 molar A minus. And I have 0.11 moles of HA in 1 liter, which means I have 0.11 molar HA. I have approximately no H3O plus at the start of this equilibrium, because again, it's very, very small amount in solution. And now, as with traditional ice tables, we write minus X on the reactant side and plus X is on the product. 0.11 minus X, 0.09 plus X, and X. Set up your Ka expression. Ka is equal to 1.8 times 10 to the minus 5. A minus, I'm going to leave off the x's, so 0.09 times x divided by 0.11. And I don't actually have this calculated out. So 1 second times 0.11 divided by 0.09. I'm going to write up here. X is equal to 2.2 times 10 to the minus 5th. And sorry, I'm trying to do this on my phone and I don't actually know where I put my calculator. And I find my pH of this solution is equal to 4.66. Now, one thing I want to talk about here is, does this answer make sense? I know there's work written all over the place, so let me pause and think about that if you need to. But I had a buffer. We just calculated that initially this buffer was at a pH of 4.74. I added 0.010 moles of a strong acid, and my pH is now 4.66, which is a pH change of about 0.08 pH units. I added the same amount of HCl, the same amount of moles of HCl to water. I saw the pH decrease by 5 pH units. What's happening? Well, it's a buffer. The buffer is able to withstand the change in pH. That's the whole point of a buffer, is to withstand that large change in pH. We should see a very small change here, which is what we see. We should not see a large change. If we saw a large change in pH, something's probably wrong with our math, or we just overcame the buffer capacity. The buffer is no longer valid at that point. The other thing I want you to notice, though, especially when you're doing these kind of calculations, is that I added acid. My pH went from 4.74 to 4.66. My pH decreased. That is correct. When you add acid, you should see that pH decrease. It won't decrease a lot, but it will decrease. If I had added base to the system, I should have seen the pH increase. So it's not going to increase or decrease a lot because you are in a buffer, but it will increase if you add base to it. It will decrease if you add acid, because pH scale is more acidic at lower pHs and more basic at higher pHs. So the common ion effect. What we just saw is an effect of the common ion effect. The presence of common ion represses ionization of a weak electrolyte. Basically, it makes X even smaller. The common ion effect is an application of Le Chatelier's principle, though. In this system, when we added strong acid, we increased the concentration of H3O plus in the system. By adding that acid, we superficially increased that acid concentration. That caused more of this to react in the reaction to go this direction, meaning less A- in solution, because it was reacted to form more HA. An important thing to note, though, is that a strong acid or a strong base can also be used as a common ion. So you need to be aware of what's in solution. I need you conceptually thinking about all times, what is in solution? What's going to react? How are these things going to interact with each other? What is going to neutralize one another? What's going to ignore one another? What's going to be a spectator? What's not? So we're teaching a lot of math, yes, because we want you to be able to calculate this stuff. But I want you in each problem to kind of step back and think, okay, but why? What's really happening? If you can understand what's happening, you will see the math never changes. The math is the same throughout all these examples, but it's really understanding why and what you have at that exact moment in time in the solution. And if you can do that, you can ace every one of these problems. What is the pH of a 0.075 molar acetic acid solution? We learned this in the previous chapter, but let's go ahead and work through it anyway. HA, meaning just weak acid, in this case acetic acid, water, H2O, in equilibrium with the conjugate base, A- plus H3O plus. It tells me I have a 0.075 molar solution, so I have 0.075 molar HA. I don't have any A- to start, and my H3O plus is approximately 0. Again, approximately, because what I really have in solution is about 10. It's really 1.00 times 10 to the minus 7th molar to start, which is so small that we say approximately 0. Minus X for change on the reactant side, plus X for change on the product side. And at equilibrium, I have 0.075 minus X for HA, X for A-, and X for H3O plus. Set up my Ka expression. Ka is equal to 1.85 times 10 to the minus 5th, and this equals X squared over 0.75. Solve for X, and I get 0.00116. Again, this equals my H3O plus concentration. Take the negative log of that value to find pH. And my pH is 2.93. What about the pH of a 0.1 molar sodium acetate solution? I know some students are still struggling with this, so we need you to be able to see this really fast in your mind. When you see something like sodium acetate, I need you to be able to immediately recognize that this is a soluble salt, which means in solution I have sodium ions and acetate ions. How do I know it's soluble? I know my solubility rules. Acetate, always soluble. Group 1 metal cations, always soluble. Therefore, it's soluble from both directions. I recognize that sodium ion would come from sodium hydroxide, a strong base. So this is a spectator. I recognize that acetate is the conjugate base of acetic acid. Which is a weak acid. So this we represent as A-, which will turn this pH basic. This pH should be greater than 7. Acetate reacts with water, and as predicted, it behaves as a base. It pulls the proton off of the water, reforming that weak acid and forming hydroxide. Tells me I have a 0.1 molar solution of acetate. And remember, if it's 0.1 molar of sodium acetate, that means I also have 0.1 moles of sodium and 0.1 molar acetate floating around in solution. I don't have any HA to start, and I have approximately no hydroxide. Again, approximately none, because at a standard neutral pH, I have 1 times 10 to the minus 7th molar hydronium ion concentration and 1.0 times 10 negative 7th molar hydroxide concentration. Change, minus x plus x plus x, equilibrium, 0.10 minus x, and x. Now I need a Kb expression. Why do I need Kb? Because I have hydroxide in my numerator. And whenever you have hydroxide in the numerator, you need Kb. So hopefully you guys have this down pat at this point, but remember Kb is equal to Kw over Ka, 1.00 times 10 negative 14 over 1.8 times 10 to the minus 5 is equal to 5.56 times 10 to the minus 10. Kb is equal to x squared over 0.10, and this equals 5.56 times 10 to the minus 10. Solve for x, we get an x value of 7.45 times 10 to the minus 6th, and again this equals the hydroxide concentration. When I take the negative log of this gives me POH. I find my POH is 5.15. Subtract that from 14 to find your pH, and my pH is 8.85. So as I expected, the pH is greater than 7, and it should be. This is a conjugate base. It's acting as a base. What if I have both of these things in solution together? What is the pH of a solution that contains both 0.075 molar acetic acid and 0.1 molar sodium acetate? In this case, the acetate ion comes from 2 different sources. We call it a common ion. The acetate will come from the dissociation of this and from being added to the solution itself. We still set it up the same exact way. HA plus H2O gives you A minus plus H3O plus. Initially, I have 0.075 molar HA and 0.10 molar A minus, and approximately none on the H3O plus. We still write minus X, and plus X for reactant versus product, but again, because I already have A minus present, less of that HA will actually dissociate. 0.075 minus X, 0.10 plus X, and X. I can set this up as a Ka expression because I have H3O plus in my numerator. Again, this requires Ka. So my Ka equal to 1.8 times 10 to the minus 5th is equal to x, not x squared, thinking about the previous example, equal to 0.10 plus x, but I'm going to ignore that x, times x over 0.075 minus x, but I ignore that x. I ignore this x, not this one. Solve for x in the equation, and I get 1.35 times 10 to the minus fifth, and this equals my H3O plus concentration. So note, 2 slides ago, so pause here for a second, visibly remember this number in your head right now, 1.35 times 10 to the negative fifth. 2 slides ago, when we did this, we saw that when I had HA present and no A minus, that my H3O plus concentration was a lot higher. It was the equivalency of 1.16 times 10 to the minus third that had actually ionized or dissociated. So I was producing a lot more H3O plus in solution. Now, I go to this example and I see that my X value is a lot smaller. That's because of that common ion effect. Because I already have a fair amount of A minus present, less of this is going to dissociate, so I'm going to have less of this present in solution, and hence the pH will be higher. I'm producing less H3O plus because of the common ion effect. Want to determine the pH of the solution? The pH is 4.87. Because less H3O plus has been produced, because less HA has been ionized, because I already have A minus present, and it wants to form an equilibrium, it's common ion effect. It's not going to form as much H3O plus when there's already A minus present in solution. It's going to form some, just not as much as it would in the previous example. So, I'm going to leave this right here so I can write this note because it's in the student notes. But notice that in this case, this is the third case, the acetate ion, CH3COO minus, comes from 2 different sources. And I'll move the screen back up in a sec, but it's really hard for me to read on the bottom of the screen. Thus, we call it the common ion effect. It's coming from the initial solution we made and plus X from the amount of HA that is being ionized. And so it's coming from 2 different places. This is your common ion effect. Another equation we can use, though, that can actually make this math easier is the Henderson-Hasselbalch equation. This is the Henderson-Hasselbalch equation. And if you just want to memorize the equation and move on, that's fine. Skip this whole part of the video. But I'm going to explain to you where this equation comes from and how we derive it. It is a mathematical derivation, okay? And so some students don't care about that at all. Some students do better when they see where it came from. So if you do better with understanding where it came from, keep watching. If not, fast forward a little bit and go to the next slide. So we're going to talk about an HA A minus buffer system. If I have HA A minus, so like acetic acid and sodium acetate, doesn't matter what it is. HA reacts with water, forming an equilibrium. I get A minus and H3O plus. If I was to write the Ka expression for this, Ka would be equal to A minus times H3O plus over HA. I'm going to rearrange this equation and solve for the concentration of H3O plus. So H3O plus is equal to Ka times HA over A minus. Next, I'm going to take the log of both sides. If I take the log of both sides, that is the log of H3O plus equals the log of Ka times concentration of HA over A minus. But you should recognize that this is pH, and this is pKa. Move up here for space. Also, a reminder for a log rule that I will never remember because it's been a long time, but if we have the log of x times y, this is the same as the log of x plus the log of y. So I can rewrite this equation to say the log of H3O plus equals the log of Ka plus the log of Ha over A minus. And I actually said this part a little too soon because that's not quite correct. It's not quite pH yet, and I apologize for that. I'm almost there. I just got ahead of myself. I am going to multiply through the equation by -1. So negative log of H3O plus equals negative log of Ka minus the log of Ha over A minus. Now I can validly say that equals pH, that equals pKa. So we're almost there. We now have pH is equal to pKa minus the log of Ha over A minus. Move up here. But another log rule that I do not remember. If you have the log of x divided by y, this is the same as the negative log of y divided by x. So we rearrange this. We say pH equals pKa plus the log of the concentration of A minus over the concentration of Ha, which is base over acid. Why do we do that? Because most often people are going to remember the plus log instead of a minus log. You can use this equation anytime. We're going to talk about the rules in just a sec, but you can use this equation anytime you have a buffer, both acid and conjugate base present. It's easiest for straight acids, but if you want to use for base, if you want to use for a base conjugate acid system, you can, but you must use pKa still. So you have to still find the pKa, and the A minus concentration is the same as your concentration of base. The H plus or acid portion is your conjugate acid. So you have to think about it from the acid perspective. This equation is valid from the acid's perspective. So, as an example, using the Henderson-Hasselbalch equation to solve the previous problem that we just did, what is the pH of a 0.1 molar acetic acid solution with 0.1 molar sodium acetate? Ha, A minus. pH equals pKa plus the log, the concentration of base over the concentration of acid. First, we're going to find the pH of just the buffer system, then I'll do it after adding the acid to it. So if I wanted to find it before adding the acid, just the pH of this system, pH equals negative log the Ka value, which is 1.8 times 10 negative fifth, plus the log of the concentration of base divided by the concentration of acid. 4.74. That is what we found for the pH of that system prior to addition of HCl. What about after the addition of HCl? We still need to set up a mole table. We cannot get away from that. So we're going to look at our H3O plus. That is going to react with our conjugate base to produce our original weak acid plus water. Remember, BCA tables are mole tables. I have 0.010 moles of HCl. In this previous example, we assumed we had 1 liter of solution. So I had 0.1 moles of A- and 0.1 moles of HA. This is the smallest number. So that's my limiting reactant. And after 0, 0.09, and 0.11 is left over. I can now plug this in. pH equals pKa plus the log concentration of base over acid. pH equals negative log 1.8 times 10 to the minus 5th plus the log, the concentration of my base, 0.09, divided by the concentration of my acid, 0.11. Now, I did take a liberty of a shortcut there. One second, I'm trying to find the answer because I can't remember where I wrote this answer down, and I don't have it written on my notes. So, 4.66, yes. 4.66 was the pH of the system. But some of you may be questioning why I'm saying here you need concentration, but I'm plugging things right in from moles. That's a shortcut I can take with the Henderson-Hasselbalch equation. Technically, yes, this equation needs molarity. But these solutions, the acetate and the sodium acetic acid, are dissolved in the exact same solution. I can go ahead and say they're in 1 liter of solution. That's fine. 0.09 molar, 0.11 molar. It's going to give me the same answers. So I'm just taking the liberty to take a shortcut. And I'll talk about the shortcut in just a sec and how how you can apply that even when it's not 1 liter solution. But what I want you to see here is that I still had to set up a BCA table. I still had to do a mole table. But it was a little bit faster to figure out the pH of my solution. You don't have to use this equation. I don't care. It doesn't make any difference to me if you do or don't. But it's good to at least be aware of the equation because it is used in the world. It is used in the professional fields. It is used in the medical field. It is used in laboratory settings. It's used in biology, chemistry, biochemistry, all the time. And so you should be aware of this equation. You should be aware of how it's used and how it's appropriate to be used. It's also just faster. Only a couple steps are cut off. I didn't have to set up an ice table. I was able to plug in, technically I should be finding molarity, but I was able to plug it right into Henderson-Hasselbalch and find the pH of the solution. You're welcome to use it. You're not required to use it. Those two slides should have been flipped. I apologize. This should be the slide that gave you a pH of 4.74, and then the previous slide giving you the pH of 4.66. Sorry, I have these slides set up so that I can do it on a whiteboard, and I tried to split up my slides a little bit to be able to do on the recording, and I sometimes mix up the order of them. But 4 key points about this equation. This equation I cannot emphasize this enough, only applies to buffer systems. There must be some weak acid and weak base present. If not, both are present, do not use Henderson-Hasselbalch. It will not be accurate. You have to have both present. They do not have to be equal. But they both need to be there. When the concentration of base equals the concentration of acid, pH equals pKa. If base equals acid, then this term goes to 1. The log of 1 equals 0, and pH equals pKa. It's really important for you to understand what that means. What that means when the concentration of acid is equal to the concentration of base. That means there's the exact amount of moles of HA as there is to A in solution. That means if I have an acid like acetic acid, say I have 100 molecules of acetic acid to start. The pKa value of acetic acid is 4.74. What that means is when the pH equals 4.74, what I actually have is 50 acetic acids and 50 acetates. They're equal to each other. pKa's can tell me a lot. They can tell me at what point is the acid willing to give up the proton. Below a pKa value, the acid will be protonated, meaning it has that proton. Above the pKa value, the acids will give up those protons. At the pKa value, it is a 50-50 shot. Half of them have given up their protons, half have not. We can determine pKa values from titration curves, which we'll do in another video, a different section of the chapter. But they're vital for us to understand how pKa relates to how likely is it for that acid to have its proton. We also see this on bases. How likely is it for that base to have its proton? Bases want protons. The pKa value gives us an indication of when it's going to have its proton and when it's going to give it up. Number 3, the concentration of base over acid is equal to the number of moles of base divided by volume, divided by the number of moles of acid divided by volume. These volumes are the same because the mixture is the same. Volume of base equals volume of acid. This is why I'm able to make this shortcut and say number of moles, because the volume is constant, so they cancel each other out. It's a good practice. I'll let you do it in my class. I can't promise you can do it in other people's. But for me, I don't care if you take that shortcut because it makes it a little bit faster. But you have to understand why you can do that. And you can't always do that. You can only do it when you're using the Henderson-Hasselbalch equation. If you're trying to plug this into a Ka expression, you have to determine the new molarity. Base, when I say base in the Henderson-Hasselbalch equation, it refers to the amount of weak base after the addition of strong acid or strong base, after the neutralization reaction, after your BCA table is complete. Acid refers to the amount of weak acid after the addition of strong acid or strong base.